Hi, so today we are going to discuss moving charge and magnetism. This is fourth chapter in your NCERT physics book, class 12. So let me start with some historical account of the topic. Okay, so in 1820, a Danish physicist, Hans Christian Oersted, while doing some demo class, to his surprise, what he observed that when he completed the circuit, a nearby magnetic compass needle get deflected each time when he did that. So the circuit was completed here, one side, and a compass needle, which is no way connected to electric circuit, kept near to only that, it get deflected each time. So there is one more such description, and it was discussed some year back in 1802 only by Jean Dominic Romagnosi. He was an Italian. Okay. He already observed this and published in a local newspaper, Gazzetta di Trentino. So, this was the thing. Now, Hans Christian Oersted did some investigations of Hans Christian Oersted. Now, before doing with it, I must tell you that since a current-carrying wire is behaving like a magnet, and we know that magnet creates a field all along it, and it applies some force when any other magnet is kept in that field. So we have to learn only two things: magnetic field created by a magnet and the force that field is applied on any other magnet kept at that point, kept in that magnetic field. So in whole this chapter we will be learning about magnetic field due to current carrying conductor and the magnetic force that the field is applying on any other current carrying conductor or any other magnet. So these two things we are to do in this very chapter. So we start with what Hans Christian Oersted investigated. So he found that when magnitude of current is increased, deflection of the compass needle placed nearby is increased. So this current carrying conductor has some effect, and if we effect at this very point, at each near point, so a field is created, and the deflection will obviously be depending on the strength of the field. So he observed that when he increases the magnitude of current through this wire, here deflection is increased, it means the strength of field at this very point is increased. Increase in current, increase in strength of field. So obviously the field will be proportional to current flowing through the conductor. One thing he observed. Now, observations. Second thing he observed that when he take the compass needle far away, then amount of deflection is reduced. Distance is increased from current carrying conductor. When distance is increased, here distance is R1, here distance is R2. So distance is increased and deflection is decreased. And deflection from where? From north-south direction, because a free compass needle is always pointing towards north-south direction. Okay. So when a compass needle placed near to it, it will be deflected by this much angle. Now when distance is increased, you can see that the needle should be directing north-south, and a feeble deflection, very small deflection is there when distance is increased. It seems that they are inversely proportional. What are inversely proportional? The strength of the field at this very point due to this current carrying conductor B is inversely proportional to distance. These two things he observed. Now third thing, when he changed the polarity of current, okay, when on changing the polarity of current was going initially in upward direction. Now when he made the current to flow in downward direction of deflection is changed. So all these observations he did, all these observations. Now on the basis of this, on the basis of observations, we have certain laws to indicate what is the direction of deflection and then what is the direction of field also, because we know the direction in which the compass needle is pointing, this will be the direction of field at this very point. So on his observations, we can make laws about two things: direction of needle of compass, and for that law for the direction of deflection of a needle of compass. And we have two rules. First one is called Ampere's swimming rule. What is this? If a needle, compass needle is there, you have a compass needle pointing north-south direction. Here red spot suggests you, red spot is for North Pole. Okay, and if you place a current carrying wire above it, such that the direction is current is along northward direction. Direction of current is northward direction. And suppose a person is swimming. A person is swimming here above this wire, above this compass needle. A person is swimming. Okay. A person above compass needle, above wire. The deflection of the needle is along his left hand. Deflection of needle is along his left hand. Now for the deflection of needle we have one more law that is called Snow rule. S-N-O-W, Snow rule. What is Snow rule? Your compass needle is there in north-south direction. It always retain in only north-south direction because of the Earth's magnetism. So it is there in north-south direction. You have a red spot here suggesting the North Pole is here. Okay. And a current carrying wire is flowing above. A current carrying wire is laying above this compass needle. Okay. Then deflection of the needle. Okay. Current is flowing from south to north. South to north. And wire is kept over the compass needle. Wire, O stands for over. Wire is kept over the needle. Then deflection will be along west. Deflection will be along west. Now, Oersted observed that the strength of this current carrying conductor at different points, that strength that we consider as magnetic field, it is proportional to current and it is inversely proportional to R. And when you combine the two, you get I upon R. And for magnetic constants are always taken as mu naught upon 4 pi. Here, okay, I'll be doing it next time, not here. Okay, so B is proportional to I upon R. So needle used to deflect somewhere, and you know, current has some magnetic effect, means it was doing like a magnet, and we know magnet has two things. It creates certain region, and in that region, if you place another magnet, the magnet will be deflected. A force will be acting on magnet. So two things only are there. A field, the field strength, and the force it is applying on any other magnet or any moving charge. Because moving charge, current, is nothing but a magnet. So these two things, field and force, we are to study in this chapter. So next topic is a magnetic field due to a current carrying conductor. Now we know that magnetic field is a vector quantity. So magnetic field, if it is a vector quantity, it will have some direction and it will have magnitude. So we will study two things. Firstly, its direction, and second, its magnitude. And for direction, you have certain laws. Like for the direction of magnetic field, you have right hand thumb rule. For direction, certain rules. first rule is right hand, thumb rule. It suggests that if you catch a current carrying conductor by your right hand in such a way that thumb is pointing along the direction of current, then your curl fingers will give the direction of field at those points. If you catch such that thumb is pointing in the direction of current, then the curl of finger will give the direction of magnetic field. At the position of fingers. Okay, suppose you are grabbing wire in this way, your thumb is pointing here and fingers is going along this direction, along inward direction, finger is going inward direction. At the back, finger is coming in this direction, okay, and then finger is coming in outward direction. So magnetic field direction is changed at all the positions. This is your current carrying wire, and here you have hand. Okay, so at this point magnetic field is inward. Here okay, at this place field is inward. As finger is going inward. At this point, field is outward. As finger is coming outward, now the field going inward is shown by a cross mark, surrounded by a circle. As the arrow going in front direction have and we only see the back of the arrow, and that is of the shape of this cross. So field going inward is represented by a cross mark surrounded by a circle, and also the current going inside. So this cross mark is shown by two things: a field inside or current inside. Now the field and current coming outside. is shown by a dot mark surrounded by a circle. And at back, third point, at back of wire, okay, here somewhere here, I am taking a dot backward. Finger is going from east to west. Fingers are going from east to west. So, field is directed from east to west. Now, this was one rule regarding direction of magnetic field. B. Okay. Now second rule, rule 2. Okay. One more related right hand thumb rule is there for circular loop. For circular loop, another form of right hand thumb rule. For circular loop. So here you have a circular loop. Now if you place the curls of your finger along the circular loop in the direction of current, then thumb will give the direction of magnetic field at the center. Okay. So this was right hand thumb rule. There is one more rule. Maxwell's corkscrew rule. Maxwell's corkscrew rule. Okay. So if you tight a screw in the direction of current from one end, from end point, then the direction of rotation will give the direction of magnetic field at each point. Direction of rotation screw or even cork also. Rotation of the head of the screw will give the direction of magnetic field at the various points. Okay, so what we learned? We learned that a current carrying conductor becomes a magnet. And if it becomes a magnet, now we need to know what is the magnitude of field it is created all along it, and what is the amount of force that field is applying on another magnet. Only these two things we are to learn in this chapter. So we will learn the amount of magnetic field due to a straight current carrying conductor, amount of magnetic field due to a circular loop, due to a solenoid, means a loop of several turns. So all these things we are going to learn. We will be learning only magnetic field and magnetic force. So we started with the law for the deflection of a compass needle placed nearby, and this was given by Snow rule or Ampere's swimming rule. Okay, and then we discussed magnetic field due to a current carrying conductor, the direction of magnetic field. The first thing, because magnetic field is a vector quantity and a vector has both magnitude and direction, so we learned how to find the direction of magnetic field due to a current carrying conductor. Now next thing, the magnitude of magnetic field due to a current carrying conductor. And this is given by Biot-Savart's law. So let me read the complete name of the two scientists. We have two scientists. One is named as, let me see, complete name, magnetic field given by law of magnetic field, also called Biot-Savart law, due to a long current carrying conductor. So these are the two scientists. Let me see complete name of these two scientists. Okay, Biot-Savart's law. Okay. Jean-Baptiste Biot. Okay. And other was Felix Savart. So these two formulated a law regarding the magnetic field of a long current carrying conductor. Here you have a long current carrying conductor, and the field at any point at certain distance will be due to the contribution of different length elements. The wire can be divided into different length elements, and you can select any one length element. This dl, length element, is a vector quantity. Okay. So the wire is divided into several length elements. One is dl, one is dl. This length element is a vector quantity. And if you multiply length element with current flowing through it, okay, it is a vector quantity in the direction of flow of current. In the direction of flow of current. So a small length, what is its magnitude? And magnitude is equal to length dl. So dl is a length vector with direction. Since it is a vector, so it has direction in the direction of current, and its magnitude is equal to the length dl. Magnitude is equal to length dl. Okay, this is one thing. Now next thing, current element. It was your length element. Length element. Now second thing is your current element. If you multiply the current flowing in the conductor with length element, it becomes your current element. This is your current element. Ideal is current element. Okay. So I am now writing Biot-Savart's law. If this is making angle theta, and this point where we are to find magnetic field B, since it is due to a small length element dl, so let me write dB. Here at a point P, which is at a distance r, position vector r from origin. Okay. So let me specify all things here. Biot-Savart's law. The magnetic field at a point P, which is at position vector r, which is at displacement vector. So let me write displacement. Displacement vector r, okay, from length dl, from length dl. Now this displacement vector and dl is making angle theta. Displacement vector and length element is making an angle theta, then according to Biot-Savart's law, the field dB will be proportional to current flowing through the conductor, it will be proportional to length element, and it will be proportional to sine of angle between the length element and the displacement vector, and it will be inversely proportional to square of distance of the point. Okay, this is your vector form of magnetic field. So dB is proportional to I dl sine theta upon r square, and the constant of proportionality in magnetism is mu naught upon 4 pi. Here mu naught is called permeability of free space. What is permeability of free space? It is the amount of magnetic field lines allowed to pass through any area or region or space is called permeability of that space. What is permeability? The amount of the extent up to which the magnetic field lines are allowed to cross through certain region. Is called permeability. Okay, so this constant will be assigning for this proportionality. Therefore, dB comes equal to mu naught upon 4 pi I dl sine theta upon r square. So this is your scalar form. Now, vector form of Biot-Savart's law. So this is dB is equal to mu naught upon 4 pi I dl cross r. You know that vector product of two vectors is equal to dl into r into sine of angle between them. So here 1 r is increased. So we need to increase 1 r in denominator also. So this is your vector form, because when you convert into a scalar form, so you again get the same thing, I dl r sine theta upon r cube. So here you can find again the same thing. So this is your vector form, and you know that a vector cross product has directions perpendicular to both the vectors. dB will be perpendicular to dl, dB will be perpendicular to vector r, so dB will be perpendicular to the plane of dl and r. Here dB will be perpendicular to the plane of dl and r. Means dB will be perpendicular to both dl and r. Now, what is differences and what is similarities between your Biot-Savart's law and Coulomb's law? Compare and contrast. Of Biot-Savart's law with Coulomb's law. Both depends on inverse square law. You can see here. Both depends on inverse square law. Means inversely proportional to square of r. B is inversely proportional to square of r. Okay. Since proportionality to inverse square, so these things are long range forces. Long range forces. You can feel this force, you can feel this magnetic field from very large distance, long distances. Now third one. What is similarity? Okay, both depends on your principle of superposition. Depends on principle of superposition. What does this mean? This means that here you could say that we obtained field for a small length element. We'll be adding field at this point due to all such length element. B1 plus B2 plus all such length element. The algebraic sum of all the fields due to all such length element gives you the net field at this point, B net, and this is called principle of superposition. So all the fields are added, all the field at any point due to various current element. When you get the algebraic sum of all those fields, you get the net field at that point, and this is called principle of superposition. So, Coulomb's law as well as Biot-Savart's law both depends on principle of superposition. Now contrast. First contrast. The source of Coulomb's force is a scalar quantity. Charge a scalar quantity, whereas source of magnetic field current element ideal is a vector quantity. Now second contrast, the force in case of the Coulomb's force is along the displacement. Whereas the magnetic force or magnetic field is perpendicular to velocity of charge, velocity and velocity of charge, okay, right, velocity of charge and direction of magnetic field. So I conclude